Okay, students, this is page 107, and right now we're just going to talk about theory. We're going to talk about linear regression. It's a major part of statistical analysis, and in linear regression, you're trying to look for a correlation or a relationship. You have two variables in regression. You have the y variable, which is the response variable or the outcome variable. You have the x variable, which is the variable that helps to explain the response, or as I like to call it, the input variable. Many books refer to y as the independent variable and the x as the dependent variable, but personally that always confused me trying to keep up with those two terms. So in my mind, I let x be the input variable because that's what I can control and that I can put into the equation, and y be the outcome variable because that's the variable that is the output, or that is what you get out of your equation. Okay? Now there are many forms of regression or regressional analysis, but we're going to be focusing on linear, where there's one y and one x. A linear correlation, if you remember from college algebra or algebra in general, when you tried to make linear equations, if you were to graph them, they would be straight lines. The same idea is here. One way you can see if two variables have a correlation is through scatter plots. In figure 1, this looks like a pretty straight line, doesn't it? What we've done is we've plotted the x on the x-axis and the y's, the outcomes, on the y-axis. And we have these dots. And if we were to take a ruler, we could draw a pretty straight line through all of these points. This is a pretty good linear relationship, and the line has a positive slope. So we say that figure 1 shows a positive, strong linear correlation. Figure 2 also looks like it makes a pretty straight line. However, the line has a negative slope. So we would say figure 2 shows a negative, strong linear correlation. Figure 3 is the same setup where the x's are along the x-axis and the y's are along the y-axis. However, it looks more like a scattershot or a buckshot pattern is what we sometimes refer to it as. There's just no way to know where to draw a line through the points, is there? It's almost impossible, unless you just have a swirly line. So we can't seem to draw a nice distinct straight line. Therefore, we would lean towards no correlation. So figure 3 shows no linear correlation. Now figure 4 has kind of a sluggish, very fat line, but there does seem to be a linear pattern or a line pattern. It's just not as skinny and perfect as figure 1 or figure 2. And it does seem to be going in an upwards or positive slope direction. So we would say figure 4 shows a weak positive correlation. Some people might call this a moderate positive correlation. The levels of strength, by just looking at the pictures, is really subjective. So we, instead of just looking at the pictures, usually will look at a correlation coefficient, R. This was designed by Carl Pearson. Now we use R to measure the strength of the relationships. R will always be between -1 and 1. If R is 1, then there is a perfect positive linear correlation. If R is -1, then there is a perfect negative linear correlation. And if R is 0, then there is no correlation. So here are some more scatter plots with their associated correlation coefficients. Here you can see a buckshot pattern, and the correlation coefficient is 0, so there is no correlation. Here the correlation coefficient is -0.3. It's extremely weak, and again, it's very buckshot. Here the correlation coefficient is 0.5, and while it is pretty scattered, it's starting to look like there might be a shape forming. Here, r is negative 0.7, and again, the dots are spread out, but the more important thing is that you can kind of see a linear shape forming. Rarely will you get a nice, tight bunch of dots, like in this example. This is a very rare case, and it's almost a perfect correlation. Here is r is 0.9, where you can see that there does seem to be some sort of correlation going on. In the real world, 0.9 is a pretty decent correlation. Here, r is negative 0.99. This is almost a perfect linear correlation. You could definitely draw a straight line through these dots, and you can definitely see that they are going in a linear direction. Now, negative correlation is not bad. Remember what negative slope means. Negative correlation simply means as x increases, y decreases. Positive correlation means as x increases, so does y. There's a formula associated with Pearson's correlation coefficient. It looks very complicated. However, if you can get the summary statistics, meaning the sum of the x's, the sum of the y's, and the sum of the xy's, the sum of the x's squared, and the sum of the y's squared, which we learned how to do in Unit 1, and you carefully plug in these numbers, it's not going to be that bad. The good news is the majority of calculators today can do this correlation coefficient for you as long as it has the data. We are going to be using the linear equation y equals bx plus a. Other books might use ax plus b. I put a hat on the y because it indicates a prediction. That's the only thing to note, is that if there's a hat, it just means y predict. You're trying to predict y, the outcome variable, based on an input variable of x. So be aware that there are two different linear regression equations floating around. We haven't quite standardized which one rules the roost yet, but our book uses this one. Linear regression and the coefficient of determination. Of course, you should read all of this, because this tells you how to get the linear equation. Anything in statistics can be calculated by hand, but most calculators can do it for you, which is wonderful. I want to talk about the coefficient of determination, r squared. It's just Pearson's correlation coefficient, but squared. And it tells you how much better, or the percent reduction in total variation, the model with the x variable fits the data. In other words, basically we say the total variation in the y variable can be explained by the model. We'll talk about this more in examples, and it will start to make sense. I have a cookie cutter interpretation for both the correlation coefficient r and the correlation coefficient of determination r squared that will help you always make an intelligent sounding interpretation.